In this video, I'm going to go through classful and classless addressing, and there is a distinction. And I'm going to go through, and through this, you're going to start learning how subnet masks affect network addressing. So to start with, classful addressing is an older addressing, and it's based on default subnet masks. They're fixed-length subnet masks that don't change, and they're assigned per address class. For example, Class A, this is the address range 1 through 127, and it's got a default subnet mask of 255 or /8. And these address classes are all the address classes for any address that you would ever get. So they're both public and private addressing. Class D is multicast, and that's for things like routing protocols, so it's reserved. And Class C is experimental, it's reserved as well. So as you go through the IP address range, you notice that where they start and where they end, and anything within this range of addresses is considered this class address, and these are the default subnet masks. And older routing protocols use classful addressing. However, the newer ones are going to classless for a variety of advantages. So to start with, classful is Class C addressing. This is an example here of Class C address. And there's the subnet mask of 24 bits and a host bits of 8 bits. So with 24 bits assigned to the network, that gives you almost 2 million different network addresses, because it's 2 to the power of 24. And the host per network address is 254. So that's the maximum number of hosts you'll get from the 8 bits. That's based on binary math. An example, for instance, is 192.168.1.0/24. That's the default mask. So if you assign this host address 1.1, the router will advertise 1.0. It advertises the network address with the default subnet mask. And here an IP address is comprised of a network portion, a host portion, and a subnet mask. So for example, 192.168.1.0, this could be subnet 1, and it's the one that's changing in that octet, the third octet. The host interface is 1.1, and there's the mask. So this is the subnet mask here, and so it's masking off the first 3 octets is the network address, and the 1 is the host address. And if you go through, you notice that the 2 changes, so that's the third octet, because that's what happens with a /24 mask. It's always the third octet that changes. And the range is going from 1 through 255, and then on to the host address and such. So it's pretty much the same thing. And here's an example here of the addressing you'd use for classful. And there's the 1.0 subnet. That could be a WAN interface. Then there's 2.0 for this subnet between layer 3 switch and router. Then this is a wireless, bunch of wireless access points assigned to VLAN 100, and it's using 3.0. Then VLAN 9 could be a data VLAN, that's 4.0. And VLAN 10 could be another user VLAN, and that's 5.0. So there are the 5 subnets. They're really top-level network addresses, but each one requires the router to route between the different numbers because they are different subnets. And then on to, say, Class B addressing, and this time the subnet mask is shifted to the left, so there are more host bits available, and there are fewer network bits available to the network address. So the number of hosts is jumped to 65,000 because it's 2 to the power 16 instead of just 254, and 16,000 network addresses. So there's no practical value for the number of hosts in any domain when you have 65,000 devices, network interfaces really, for a segment or a broadcast domain. So it's just not practical. And there's, for an example, of 172.16. That's within that Class B address range. It's at /16, so that's the top level address, 00. And then the host address is an example B 1.1, for example. And the advertised address would be the network address. So it would be 0016. It'll actually, as a classful address, it will advertise the network address on a class boundary. In this case, because it's 16, it would take the first 2 octets, and that's what's advertised. So you can have a lot of different addresses, and it gets summarized to 172.16, and that's what's advertised. And again, this is the example of the subnet. So 172.16 is the network address, as you can tell right there, and 1.1 is the host address. And what happens, so 17 would be the next one, because with Class B default, it's Class B, it's a classful addressing. So now it's the second octet that's changing and becoming a new subnet, and you could do that 1 through 255. And there's an example of another host address. And here's an example of the addressing. So there's 172.16, there's 17, 18, 19, and 20. And that's the subnets. And then with Class A now, the subnet mask is shifted right further over to the left now. And it's got 8 bits for the network, so there's only 128 network addresses. So that's impractical. You're going to need a lot more today than that. And the hosts are 16 million. So that's you'll note that as we go through, there's no practicality to it. If you're using it as classful, I mean, it's something you really have to subnet to use it in a practical way. So the network address will be 10, because there's the .8. So it's now subnetting the first octet. So the host address will be this one here, 10.1.1, and this is what's advertised, 10.0.0.0/8. So as the network portion, you can tell now there's a 10 subnet and an 11 subnet. And so it goes through them pretty fast, really. And that shows you how it's masking off the first octet. So 10, 11, 12, etc. In classful addressing, there's a 10, 11, 12, 13, and 14. So on to classless VLSM. This is variable length subnet mask. So now the addressing uses variable length subnet mask. You don't have to use the default mask. You can move that subnet mask to the left or to the right. And so what it does, it creates multiple subnets from a network address. So you can take a top level network address, and it's subnetted when you're using VLSMs to create a bunch of separate network addresses from a single network address. And you can manage the IP address space a lot more efficiently and adjust it from the number of hosts you want. And you can use multiple different length subnet masks within the same network and multiple networks. The routing table is a lot smaller. It's a lot more efficient, as mentioned. And this is accomplished by advertising the subnet mask in the routing updates. And so it goes into the routing table, so you get a much better routing table, much more effective, much more optimized. But it is advertised with the routing updates, and that's what makes it exclusively different from Classful. OSPF and ISIS support only classless currently, and the older ones, ERGRP and RIP-v2, support Classful and Classless, so you can select either. Typically, as your network gets larger, you're going to use Classless. And here's an example here. This is a Class C address, 192.168.1.0. And what happens is, from this one address, it's subnetted, so you still got the one there, but it's using some of the bits in the last octet to create new network addresses, .8, 16, 20. Now these are network addresses, so the first host address would be 1.9, or here would be 1.17. This is where you get the host addresses from, and it moves from one range to the next. So VLSMs, for example, here's 24 bits, so we know that's a Class C default mask with 8 bits and 24 bits network. Now if I move this over to include 2 bits in the fourth octet, so now I've only got 6 bits for the host, and 2 bits I'm going to use for subnetting. And that's basically all it is. It's just moving it into the octet where typically host bits are assigned. So you can take something like this 1.64. That's something that's subnetted from the one dot address, and 65 would be the first host address available, and the 64 network address would be advertised like that. In the IP address components, for example, kind of the same thing. That 64 is the subnet address, 65 is the first host address. It's using a /26 subnet mask, so it's moving 2 past the 24 to include some bits into the fourth octet. And there's the mask. And the next one would be, the next subnet would be 128. So the last host address there would be 127, and 128 starts a new subnet with 129 as the host interface address. And here's an example here. I can use /30, giving me only 2 interfaces here, 2 host interfaces. /30 takes the subnet mask right over to the right, so there's very little left of the fourth octet. And I can assign /29. That gives me a few more hosts for some redundant links for network interfaces. And then the 16 is gives me a lot more subnets for various wireless subnets. You can group 10 of them into one subnet, 10 into another. And 27 and 26, those are more hosts, so you can get more from 26. You can get more hosts and fewer subnets. And that's basically what I'm doing by changing the subnet mask. This is all on the same network. So those are what's bolded here, those are the actual network addresses that I've created from that one dot address. I'm going to go to class B. It's the same thing. I can move any bits I want, into the fourth octet, right up to practically /30. This is a 29, so I've got 3 host bits, and that would leave me with well, if I got 16 there, 16 and 13, so I'm using 13 bits into here, and 3 for the host bits. So for example, 172.16.1.8, that's a network address. It's a /29, so I'm subnetting into the fourth octet again. And 1.9 would be the first host address, and 1.8 is what's advertised. And here you can see that 1.8, 1.9 is the first host interface. And here the next subnet range would start at 16. And I'll talk about multiples and where it starts at. The multiple is based on where the subnet bit starts at. So that's the host address, 172.16.1.17, and that's a host interface, and 16 is the network address for that range. And here's an example of class B addressing, 172.16.1.4. So it's its fourth octet where I'm getting the network address now. The .4, .8, .16, .32, 64. They're multiples, and within each range. And I'll go into a little bit more about that. It'll make more sense. And for class A, there's the 8 bits. That's the default mask with 24 host bits. And this time I'm moving from 8 bits, I'm moving to 27 bits. So I'm moving right into the fourth octet again. I've only got 5 bits, so I'm using the rest of the bits for host bits for subnetting purposes. So I'm going second, third, and fourth octet. So it's quite a bit there. Quite a few subnets that I can create from 27 bits instead of 8 bits. And that's the reason why I'm doing it, because I don't need this many hosts. I just need a few. And I'm using a 27 here. So 1.32 is an example of one of the network addresses I can get within /27. And then there's the host address 33, and what's advertised is 10.10.132, the network address. And here the subnet is 32, and there's 33, my first host interface. Then 64 would be the next one, and 65. And pretty much shows you here the 33 is the host number, and 10.10.1 was the network address. And addressing is the same thing. I've got variable masks based on the number of hosts I want to that are required for each VLAN, and that's pretty much all there is to it. This time I'm just using a Class A address to do the same thing. Class A is 10 dot is where you'll find most of the private addressing for a lot of the companies, because there's just so much you can do with a Class A. And subnet mask shifting, I've kind of talked about this already. I'm using a non-default subnet mask for an address class, and so I'm just shifting bits over into this fourth octet. This is /27, so 8, 16, 24, 25, 26, 27. So these 3 bits here I'm using for subnets to create a bunch of subnets, and these 5 bits left are for hosts.